Hi guys, so now we'll be looking into the integrator, which is an application of operational amplifier, and integrator, as its name suggests, will produce an output which is equal to the integration of the given input signal. And this is the circuit of integrator, and we'll be applying V in, which is the input voltage, and the point A is connected to inverting terminal and B is connected to non-inverting terminal and to the ground, and the feedback element is CF, and the output will be V0, and the resistance in the input is given as R1 and the current through it is given as I. So here I is equal to V in minus VA by R1 and V in by R1. So here VA is at virtual ground, so the I will become V in by R1, and the output will be getting I is equal to CF into d by dt of VA minus V0, and this will make it minus CF into dV by d0, dV0 by dt. So since VA is 0, this becomes dV0 by dt, and equating these two equations we get Vn by R1 is equal to minus CF dV0 by dt, and so integrating both of these we'll be getting V out is equal to minus 1 by R1 CF integration 0 to t V in dt plus V0 of 0. So V0 of 0 is constant, and R1 CF is the time constant of integration. So the output is now directly proportional to V in, which is the input voltage we provide, and since negative sign is there, it is proportional to negative of V input voltage, and V0 is also inversely proportional to R and C, which are the resistance and capacitor which we provide for the circuit. So if the input is sine wave, its integration is cosine wave, so we'll be getting cosine wave at the output. If the input is square wave, the output will be a triangular wave. So for accurate integration, the time period of the input signal must be longer than or equal to RC, and this is the waveforms of the integrator. Here the input voltage is given as A for t greater than or equal to 0 and 0 for t less than 0. So this is the input waveform, and integration of this V input will produce an output minus A into T, and the graph of this is this. So if we apply this input voltage, we'll be getting integration of the input voltage which is V0 is equal to minus AT. And if the input waveform is square waveform, which is A with whose value is A from 0 to T by 2 and minus A from T by 2 to T. So the integration of it will produce an output minus AT from 0 to T by 2 and plus AT from T by 2 to T, and its waveform will be a triangular wave. So if we apply a square wave as input to the integrator, the output will be a triangular wave. And if we apply a sine wave, Vm sine omega t as input, then we'll be getting Vm by omega cos omega t as output. And here since we are integrating sine omega t, we'll be getting Vm by omega cos omega t, and the minus is for integration of sine omega t, and this minus is for applying it in inverting terminal. And practical integrator is to reduce error at voltage of the output. So there will be differences between the ideal integrator and practical integrator. Here RF is connected across the feedback capacitor, and RF limits the frequency gain and hence minimizes the variation in the output voltage that we'll be getting from the integrator. So both stability and low frequency roll-off problems can be corrected by the addition of resistor RF in practical integrator. So in order to reduce the errors in practical conditions, we'll be adding RF, which is resistor for feedback connection in the integrator to reduce the error.